we'll be talking about linear programming. When we have linear equalities, for example, let's say 4x plus y equals 20, 2x minus 3y equals 6. These are examples of linear equalities, and I hope that you know at this point, but we solve these kinds of equations using maybe the Gaussian elimination method or solving graphically. We could also solve simultaneously, right? But when we have linear inequalities, for example, instead of equals 20, we have less than or equals 20, which is written to mean that 4x plus y is at most 20, right? Or you have greater than or equals 6, which is written to mean 2x minus 3y is at least 6. This is solved with linear programming. These kinds of inequalities would be solved with linear programming. So when we solve linear programming, we want to graphically find a point which lies in the intersection of all of these linear inequality regions. We also have a constraint in linear programming. An example of a constraint, you could have, you want to find the maximum of x plus y or the minimum of x plus y, as the case may be. So a problem in linear programming usually looks like this. First of all, you have your constraint. Let's call it, for example, our constraint, we want to find minimum of minus x plus 4y. And we have our linear inequalities. For example, it could be written like this. That plus an xn less than or equals, let's say less than or equals b1. We can have a to x to 1 plus that a, this is 2 1, n1 x, that all the way. You just have a form of linear inequality. So we use linear programming to reduce or to model other problems, and once we have reduced those problems into a linear programming, that means into a linear inequality, we can then solve the problem using linear programming. So that means when you have more complex problems, for example, we can use linear programming to solve problems in optimization, in scheduling, as we have talked about in previous videos, resource allocation, as we talked about in previous videos, machine learning, data mining, even in operations research. We use linear programming to model these problems. Linear programming is just, a mathematical method used for finding the best outcome in a given model. So you have the problem you're trying to solve, then you check if you can model it as a linear. You can model it in such a way that it can be solved with linear programming. So what that means is you want to examine the problem. You want to find out whether the problem has a constraint, whether it can be expressed as linear inequalities. If yes, then this problem can be modeled as a problem that can be solved with linear programming. So the requirements and the objectives for problems solved with linear programming are linear relationships. And it's particularly useful when we need to make the best decision in a scenario involving several other linear inequalities or equations, as the case may be. So in essence, we use linear programming when we have a linear objective function that we want to either maximize or minimize, subject to a linear constraint. So it's applied in computer science and beyond. We are going to grab our first example, and in this example, we want to solve a network flow problem, but we are going to model it as a linear programming problem. So let's get that real quick. Let's consider this diagram. We treated network flow just before this topic, just in case you missed it and you want to take a look. So this is our source, these are nodes, and this is our sink T. So we have edge 1, or you can call it X. This is 100. It goes this direction. We have edge 2. capacity 100 goes this direction. We have edge, let's say we have another edge here, right? Let's say this is edge 3, capacity 1. Edge 4 goes this direction, capacity 100. Edge 5 goes this direction, capacity 100. If you've not subscribed to my channel, please remember to subscribe. It's totally free. That is, if you like this video, if it's informative. Okay, so this is a network flow and we want to model it. We model this as a linear programming problem. That means we want to find the constraint, and once we find the constraints, we want to express all other conditions as linear inequalities. So what are the constraints? Let's look at this. For the purposes of this question, each edge, let's call each edge, let's say edge I, let's call it xi, So we want to call every ei xi. So first of all, we want to set up an objective function. So what is the objective for a network flow problem? What's the objective? The objective is to send the most capacity to the sink, right? So that means we want to maximize x4 and x5. If you remember from we treated network flow problems before this. So if you can remember, our objective always was to transport the most capacity from the source to the sink. So that means if you interpret what I've just said mathematically, it means we want to maximize, right? So our objective function is to maximize x4 plus x5. This is our objective function. And the next thing we do is we find out what the constraints are. So for the network flow problem, we have two kinds of constraints. We have a flow constraint and we have a capacity constraint. That is, each edge has a constraint. For example, for edge 1, I can't transport more than 100, right? I can't transport 120 because edge 1 can only, transport 100. So that's a constraint, right? So now let's talk about constraints. We have two kinds of constraints for this problem. We have two kinds of constraints. We have the first one, we have a capacity constraint. And for a capacity constraint, we have x1 less than or equals 100. As you can see here, we have x2 less than or equals 102, x3 less than or equals 1, x4 less than or equals 100, x5 less than or equals 100. We also have a flow constraint or flow conservation, as the case may be. And in the network flow problem, we said that for the flow constraints, we want our incoming flow to be equal to the outgoing flow, right? In equals out. So that means if you look at this diagram, we want x1 to be equals x3 plus x4, if that makes sense, right? Because whatever it is goes from the source through x1 cannot be more than what goes out at that same time through x3 and x4. So we have x1 equals x3 plus x4. And what else? Let's see. x2 plus 3. This is x2 plus x3, right? It cannot exceed what goes out through x5. So we have x2 plus x3 equals x5. And what else? I think that's it. So we also have that x1, x2, x3 up to x5 would always be greater than or equals 0. So we have x1, x2, x3 to x5 will always be greater than or equals 0. So now we are going to solve this problem at this point with an LP solver. We have a lot of LP solvers online available free of charge. So when you solve with an LP solver, you want to enter all of these constraints and your objective function, and then it automatically solves it for you. But merely by eyeballing the equations, the inequalities and equations we have right now, we can say that a possible solution for this, let's say the possible solution is x1 is equals 100, x2 is equals 100, x3 is equals 0, x4 is equals 100, and x5 is equals 100. We notice that when we go with this solution, right? When we go with this solution, everything here works. Everything here works. So with your LP solver, you could get a variety of solutions. But the most important thing is that for every set of solution you get, it's going to satisfy all of these objectives, constraints, and everything. Everything is going to be satisfied. So we are going to end this video here. If you did like my video, make sure to subscribe, and I'll see you on the next one.